Okay, so let's do another Cramer's rule example. So here's our matrix A right here. We have a different matrix A than before. And here is our vector B, and we want to solve for x in this equation, right? Ax equals b. We want to solve this system of linear equations, in other words. So by Cramer's rule, x1 is going to be n1, the determinant of that, divided by the determinant of A. Okay, so what's n1? It's just like matrix A, but column 1 is replaced with vector B right here. Okay, so you see that right there. We get those two determinants. We have a negative 29 on the bottom, and at the top we get what we get, and eventually the result is 61 out of negative 290. Okay, so that's how we'll leave it, right? We won't be reducing that any further. Okay, and then x2, it's going to be n2, the determinant of n2 divided by the determinant of A. We already know the determinant of A, negative 29, and so we just need the determinant of n2. Now notice n2, it's just like matrix A, but now it's the second column that's replaced by B. Right, there's our vector B right here. Okay, so we go through that process and we get 18 out of negative 145 as our second component, right? So there's our x. We solved our equation. 61 out of negative 290 and 18 out of negative 145. Now, so we have different ways to solve such an equation, right? So we can use row echelon form, we can use reduced row echelon form, we can use A inverse, right? These three methods we went through in the first part of this pair of videos. And then we have Cramer's rule, right? So we already used Cramer's rule in two different ways, okay? So now we can always check things, right? So 3, 7, 2, negative 5, right? That's our matrix here. That's our vector B, negative 3 over 2, 1 over 5. So this is the x that we found, okay? And it seems like pretty unusual numbers, right? Because, well, the numbers in matrix A are pretty simple. The fractions in vector B are simpler, right? So always good practice if you have the time on the test, why not check things, right? So let's try it. Let's do A times x and see what we get, okay? Well, this is what we expect to get, right? Because that's vector B. So let's try it, okay? We do our multiplication of a vector times a matrix times a vector, right? So we have 3 times the first component plus 7 times the second component, which gives us negative 3 over 2, as expected, okay? Then for the second component, we do 2 times negative 61 over 290 minus 5 times negative 18 over 145. And going through that calculation gives us 1 over 5, again, as expected. Okay, so always a good thing to do those checks. Now let's do one more example let's do an example that's 3-dimensional here. Okay, so there's our matrix A, there's our vector B. We want to solve AX equals B, right, to find that vector X. So again, we're going to need a bunch of determinants to use Cramer's rule. So let's find the determinant of A, right, which is going to be the determinant of what's in here. All right, now first thing is we can switch these two rows, right? So we can switch the bottom row and the top row, and that's actually going to change the sign of our determinant. So now negative determinant of A is going to be the determinant of this value here. Okay, then we can do a row operation, which isn't going to change the value of our determinant, right? So eventually we have negative determinant of A is negative 195. So the determinant of A is 195. Okay, we'll also need N1, N2, and N3. Okay, so let's start with N1. Okay, there's our matrix N1, just like A, but the first column is replaced by B, right? There's B right here, 1, 2, 3. Okay, and so we look for the determinant of that, and we get determinant of N1 equals negative 91. Now here we're using row operations to create two zeros here, which makes it easier to find the determinant, because then we just have 1 times the determinant of that. Right, there it is. Then for N2, we'll switch two rows again. Right, so we're looking for the negative determinant of N2. Right, having that 1 there is convenient, because again, we can use row operations to create zeros here, and the determinant is just going to be 1 times the determinant of that. Right, there it is right here. And so we get the determinant of N2 is 91 rather than a negative 91. Right? And by the way, we use that method here as well for finding the determinant of A. Right? We used row operations to create two zeros so that we have 1 times the determinant of a 2 by 2 matrix. All right, so N3 is left. Okay, again, we will switch two rows. All right, so that we get a 1 up here rather than down here. So we're finding the negative determinant of N3. And again, we use row operations to get those two zeros. So again, our determinant turns into 1 times the determinant of this matrix there. And that gives us negative 13, right? Now that's the determinant, that's the negative determinant of N3, right? So the determinant of N3 is going to be 13. And now we can get our three components, okay? X1 is going to be the determinant of N1 over the determinant of A. So that's negative 91 over 195, or negative 7 out of 15. That's what that reduces to. For X2, it's going to be the determinant of N2 over the determinant of A. So positive 91 over 195, or positive 7 out of 15. And for X3, it's going to be the determinant of N3 over the determinant of A. So 13 over 195, or 1 out of 15. So there's our matrix X right there. Negative 7 out of 15, positive 7 out of 15, and positive 1 out of 15. And again, it's good to do that check. Okay, so for the first component, we're going to have 2 times x1 plus 3 times x2 plus 8 times x3, which gives us this long expression, which eventually leads to 1, which is the first component of B, right? Because remember what we're solving for here, right? It's AX equals B, right? So we want the results to be the components of B, right? So that's what we have for component 1. Let's try for component 2. Okay, so we have 5 times, right? There's a 5, 9, and 2, right? So there's our 5, 9, and 2, right? 5 times the first component of X, 9 times the second component of X, 2 times the third component of X, and eventually that gives us a 2, which is exactly what we want, right? The second component of B. And the third component of X, right? We're going to do 1 times the first component of X times 7 times the second component times 3 times the third component. That should give us the third component of B, which is a 3. So let's try that. Okay, so 1 times negative 7 out of 15 plus 7 times positive 7 out of 15 plus 3 times 1 out of 15, and that gives us a 3, just as expected. So that's Cramer's rule. That's another way to solve matrix equations or systems of linear equations, provided that the determinant of A is not 0, which is like saying provided that the inverse of A exists. So that adds to your collection of ways to solve these kinds of equations or systems of equations. So until next time, enjoy.